So J.J. Thompson, so this is after Dalton, 1856 to 1940. Again, I'm not going to test you on these scientists' names or the dates, but I think it's helpful to acknowledge them and just to see how this came about. He discovered a smaller particle called the electron. So this was a big deal because atoms were supposed to be indestructible, right? And how could you have something smaller inside of the atom? So that was a big deal. He found that the electrons he discovered were negatively charged. They were much smaller and lighter than the atoms, and they were uniformly present in many different kinds of substances. Every substance he tried, he could find electrons in. Okay, so electrons seem to be common to all atoms. So, well, what's going on inside the atom then? We know there's electrons. They knew that atoms were neutral. They did not have an overall charge. So if the electrons are neutral, there must be something positive. So he came up with what's now called the plum pudding model. In the United States, we're not familiar with plum pudding. It's an English dessert. It doesn't sound real good to me, but, that's a cultural thing. It's okay. So the closest thing we probably have is like a blueberry muffin. So if you think of a blueberry muffin, and the red here, the sphere of positive charge, would be like the muffin part, and the electrons would be like the blueberries, and they're just kind of randomly distributed within the muffin. This was his model. You got to start somewhere. Kind of maybe dorky, but I'm sure we couldn't have come up with any better at that time. So Rutherford was trying to show that this model was correct. So now we're in 1909, Ernest Rutherford. He was trying to investigate this atom and the electrons. And so he took a very thin sheet of gold foil and an alpha particle source and passed through alpha particles at this thin sheet. Most of the particles went straight through, and that's really what they expected to happen. A few were deflected at small angles, but some of them were deflected at sharp angles. And so this told them something about what was going on inside of the atom. So this is what they expected to happen, that these alpha particles, which were much smaller than the atom, would just go straight through. That's what they expected. What actually happened, though, was that some of them bounced back. And Rutherford said that this bouncing back of the alpha particles was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. A 15-inch shell. That's a bullet that's 15 inches long. From a cannon or a mortar or something, right? You shoot that at a tissue paper, piece of tissue paper, like in a present, that thin tissue paper. It's not going to bounce off, is it? It's going to blow straight through. You'd be really surprised if it came back and hit you in the face. You'd be dead too, but, you'd be surprised before you were dead. So what on earth was causing these particles to bounce back? There's got to be something in there that's pretty massive for these particles to bounce off. So this led to a new model of the atom, the nuclear model. So he proposed to explain these results, that there's a nucleus in the center, and that is where most of the mass of the atom is located. By now they had detected some other particles in the atom as well, in addition to the electrons. And so protons and neutrons are here in the nucleus. And because this nucleus is very massive, if we got a direct hit or a close hit on the nucleus, the particle would bounce back. The other particles would go through if they missed the nucleus. So that's the idea. So the nuclear theory of the atom says that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of an atom is empty space, through which tiny negatively charged electrons are dispersed. It doesn't say exactly what those electrons are doing, they're just in there. And the third point is that the number of negatively charged electrons, which are outside the nucleus, is equal to the number of positively charged particles inside the nucleus, so that the atom is electrically neutral. So electrons are negative, and the positive particles are called protons. They have the same magnitude of charge, but one's negative, one is positive, and so you have to have equal numbers of them. We need to be familiar with these ideas to continue understanding chemistry, but I will never ask you to write out the 3 premises of the nuclear theory of the atom. Okay, I don't believe in having people just regurgitate stuff like that, but you should be familiar with these ideas. So, later work showed that in that nucleus, in addition to the protons that Rutherford knew about, there were also neutrons. So the protons are positive, both those words start with P. Neutrons are neutral, they both start with NEU, and the electrons are negative. This dense nucleus makes up more than 99.9% of the mass of the atom, but only occupies a small fraction of its volume. The electrons are much smaller, and they're distributed throughout this big empty space. So they occupy a large space, but they don't have much mass. So one way to think about electrons is they're like water droplets in a cloud, or in the fog that we get here in the winter, right? You can see the fog, right? It's hard to see through the fog, and people have accidents and stuff because of the fog. But you can walk through the fog without problem, right? Because the droplets of water are really, really tiny. It's mostly empty space, but those little droplets of water obstruct our vision. And so that's what the electrons are like. They're like water droplets in a cloud. They're taking up a whole bunch of space, but they themselves are very tiny. Just to get an idea for how big this is and the relative sizes. So if the nucleus was the size of a pea, a green pea, and you set that on the 50-yard line of a football field, okay, the edge of the atom would be at the end zones. So the nucleus is the size of a pea in a football field. It's mostly empty space. Yes?
Are the electrons so widely dispersed only because the nucleus is positive, so they're repelled, or are there other properties?
The reason that the electrons are so dispersed is a very complicated thing to explain. I will attempt to explain some of it. It has to do with quantum mechanics and some ideas that scared Einstein. So I will be teaching you about electrons and what they're doing. You are not going to completely understand what they're doing because nobody does. It's very complicated. Yeah. If you like to blow your mind, that's a great thing to study. To understand how dense the nucleus is, so we've got a picture of how small it is relative to the size of the atom, right? A football field with a green pea in the middle. If you were able to just take the nuclei out of the atoms and just put them all together, and you made something the size of a period on a printed page just out of nuclei, it would weigh millions of tons because you took out all that empty space. So the nucleus is incredibly dense.